Life is good because it's physics time once again. We have just looked at electric fields. We're now going to look at capacitors. What are capacitors? Well, capacitors are objects in a circuit which have a quality called capacitance. Well, what's capacitance? Well, it's what capacitors have. Now, capacitance actually it's all to do with storing charge. If you have two big sheets of metal, like perhaps a couple of oven trays, and you were to put a voltage across the two, you could store charge. You could store charge on these two plates. So capacitance is the ability to store charge. In fact, it's the amount of charge stored per unit potential difference. Now, if that sounds confusing, think of it like this. Capacitance, measured in farads, after Faraday, Michael Faraday, capacitance is charge stored, Q, per unit potential difference, or charge stored per volt, if you like. That's really how you define capacitance. It's the amount of charge stored per unit potential difference. So, in a circuit, by the way, in a circuit you never find capacitors that look like two oven trays. Nowhere in the universe will you find capacitors that really look like two oven trays. But that's actually what they really are. Well, they're not oven trays, but they are sheets of metal separated by a small distance. And the reason they don't look like this is because they're rolled up. They're rolled up very small, but in actual fact they've got quite a large area. So in a circuit you will typically have something like this. You'll have an energy supply, you'll have some connecting wires, you'll have a resistor, and you'll have a capacitor. And it's quite useful to have an ammeter and possibly a switch. Now what you're going to notice is if you turn your power on and you measure the current, if your resistor is a decent sized resistor and you've got a good sized capacitor, you will actually measure a current flowing around here. Conventional current, remember, is the flow of positive charge, even though actually we know it doesn't really exist. It's actually the flow of negative electrons this way. But you know, we all know, we play the game, we think of it as conventional current, the flow of positive coulombs in this direction. So how can current flow when you've got this great big gap here between the two plates and a capacitor? I'm glad you asked. It's a bit tricky. Well, what happens is, as soon as you flick your switch and your power goes on, these imaginary positive coulombs want to spread out because they can. They want to spread out and get away from each other because like charges repel, and a whole bunch of them accumulate here on this plate. And a potential difference begins to build up. Now, what happens when a whole lot of positive charges accumulate on this plate? They repel any electrons that are here, and they attract any positives that are in this wire. So what we actually get is the flow of positives around here. It induces an electrostatic current in this side of the circuit because it repels the positives which go this way and attracts electrons which come this way. So whatever current you have going this way is also going to be the same current on the other side. So your ammeter is going to measure a decent sized current quickly reducing, eventually reaching zero. It reaches zero when the potential difference on your capacitor is equal to the potential difference in your supply. And at that point the potential difference in your resistor will drop to zero because the current through it will be zero. Okay, what sort of factors determine the size of the size of the capacitance? Remember, capacitance is the ability to store charge. So remember, you've got your two plates. Let's just draw them like this. That's the symbol for a capacitor. Now, what does capacitance depend on? Capacitance depends on, you imagine the bigger the area of the plates, the more charge can be stored. So area, capacitance is directly proportional to area. Capacitance is also going to be less and less effective if your plates are further and further apart. So it's inversely proportional to the distance between them. But of course, in any equation like this, you need a constant of proportionality. So In this case, it is our good old friend epsilon naught, which is the absolute permittivity of free space, which happens to be 8.85 times 10 to the minus 12 coulombs squared per Newton per metre to the negative 2. Wow. Sorry, per metre squared. So that is our equation for capacitance. Quite useful. The bigger the area of the plates, the bigger the capacitance, the further apart they are, the smaller the capacitance. Now what happens, let me just rub this off, when we get capacitors in circuits, we often combine them. Now, you can combine capacitors in series or you can combine them in parallel. Now if you can combine capacitors in series, we're used to seeing this with resistors, where in series resistances just add together to give you a total resistance. Well, capacitors are the exact opposite. With capacitors, 1 over capacitance in series total equals 1 over C1 plus 1 over C2 plus 1 over C3. You can show it mathematically, but basically the idea is each of these gaps is effectively just making one capacitor with the same area but a really big gap. That's effectively what it's doing. Because you can imagine these ones in the middle do nothing, or this one in the middle does nothing, and you've just got a plate here and a plate there and a bigger gap between those two plates. So effectively you've got one capacitor with a bigger gap. Now capacitors in parallel, let's just draw 2 of them because I run out of space. Draw 2 capacitors. 2 capacitors in parallel, when you think about that, that is really the same as one capacitor with a bigger area. You get the area of this and the area of that, you add them together, they're both the same distance apart, that just makes one capacitor with more area. So in actual fact, what we see is capacitors in parallel, the capacitance of 2 capacitors in parallel just equals C1 plus C2. And if you've got more than 2, C3 plus, on we go. They just add together like that. Okay, isn't that good? Now you understand. Finally, let's talk about the amount of energy that can be stored in a capacitor, because capacitors store charge, and we know that stored charge, that energy is stored when charge is stored. So you imagine charging a capacitor. You are going to have a potential V across your capacitor when it's fully charged, and it's going to have a charge Q. But of course it starts with 0 charge and 0 potential across it, and it gradually builds up. So by the time you've got Q coulombs, you've also got V volts. But we know that I'm just going to have to pause there.